I want to tell you that maybe I've said too much, maybe. I really have enjoyed being a teacher this year. I know that some of you said, couldn't you have been a little easier on us? Could have or should have. I mean, I don't know. I don't think it's the job. I don't think it's my job to just make sure I'm easy on you. I'll try to, like I said, near the end of the year, we'll just be doing labs, so I'll do that for you. All right. Well, anyway, we found out, and you had all these words, and Carson, what we did was, I asked him one day when he first started, I said, tell me everything you think has anything to do with a blank screen. No, I didn't ask him that. I said, tell me everything you think might be associated with nuclear chemistry. And they came up with a list that had maybe 20, 25 things, and we'll probably touch on all of those. I'm hoping we get to touch on all of those before. and so we started working on that a little bit. Is that up there yet? Nope. Anyway, so here's some of these terms they came up with, and you can see like nucleus and half-life, fission, fusion, mushroom cloud, chain reaction, atoms, mutations, and we've already touched up on some of those. But let's go to this page here. This is it's on the packet with the. By the way, this symbol right here, that was an international symbol for radiation. I was talking to Tim the other day. One thing I didn't understand at all was I'd heard the word radiation before. Remember the electromagnetic radiation? What's another word, a common word that means electromagnetic radiation? Starts with an L. Light, right? That's radiation. Right. And some radioactive things do give off light. But my voice is radiating. That's radiation. But when you talk about nuclear chemistry, the kind of radiation they're talking about is called ionizing radiation. And what that means is that these things have the ability to knock electrons off of molecules or atoms and therefore cause a cell to maybe even die. And if you get enough molecules that are disrupted or they become ionized, then the cell dies. A lot of cells die, then the organism dies. And so that's called ionizing radiation. So every time I use the word radiation here, it's probably going to be something that can cause harm to living things. Now, we also learned that when you're trying to balance a nuclear equation, you have to balance the top numbers and the bottom numbers. So let's take a look at the first one. See if you can figure out what's missing. Take a look here. I'll do the first one with you. 10108, the isotope 10108, and captures, oh wait, notice what I did here? What side of the arrow did I put the beta particle on? If I put it on the left side, it means it was bombarded with it, or it captured one. But what if I put it on the right-hand side? What does it mean? That he what? It gave it off. It emitted it, right? That'd be radiation, wouldn't it? But I'm going to radiate it. I'm going to radiate you. And then you might capture this, and let's take the top set of numbers. 108 plus 0 is what? Okay, I don't know who you are yet, but I know your mass is 108. Bottom numbers. 50 minus 1. Okay, let's take a look at the periodic table now. Number 49 is indium. That's weird. Indium. I don't get to say indium very often. All right, got that? So look what happened here. They caused this element to, whoops, did I say indium? Yeah. It caused this element to drop down to indium. It was transmuted, wasn't it? It was transmuted in indium, yes.
How is the electron not repelled by the
Okay. Man, that's a great question. If you said, I'm going to throw some electrons at your nucleus, and well, first of all, how are you going to get by all of 10's normal electrons? They're all negative, right? I'm going to fire a negative bullet, and there's going to be 1 layer, 2 layers, 3 layers of electrons. How are you going to get past that? And what they do, many times, they take these atoms, and they strip them of all their electrons. Oh, now you just have the nucleus. You see that? So you just have the nucleus. They can do it that way. Or if you have a particle accelerator and you can accelerate it high enough, it can overcome the repulsive forces. Because they sometimes slam whole lithium atoms. I'm going to accelerate a lithium atom and shove it at another nucleus. Well, here's proton, 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 proton. That's another thing. See that? If you get it going fast enough, then it'll go. If you don't, it'll go whoop. It'll just repel, won't it? And that's why the particle accelerators have to be, it's very fine-tuned, and it has to be high speeds. You have to really accelerate them. I would have to look into every time they do this, which way they did it. Was it just high energy beta particle, or was it you stripped the electrons off at the beginning with and did it? All right, let's do the next one. It says here, did a mass change occur? Did a mass change occur? No. So if you bombard something with something that has no mass, then I wouldn't expect a mass change. Did the atomic number change? What do you think? Yes, so did transmutation take place? Yes, it's a new element, isn't it? Try the next one. Iron 50 decays into cobalt 50. What's it going to emit? Notice the word decay. Notice that I start with one thing. On the right-hand side of the arrow, it's going to turn into at least two. At least two. See if this works for you. See if you can do the nuclear equation. So 50 has to equal 50 plus what? Okay. 26 has to equal 27 plus what? And then I go down to my list of characters, and I find out that that is a beta particle. Now, I will tell you that some of the older books, they like to do this. They like to use the Greek letter beta, they put a little tail on there, and they'll do this. So if you ever read a book and they have actual beta, but really it's an electron that comes from the nucleus. And that's why we don't call it an electron, because it's an electron that comes from the nucleus. So some books will say that, some books will do that. All right, does everybody get that? Did everybody get that one right? It says, what's the difference about a nuclear equation in which a nucleus is bombarded from one in which it decays? And look at this here. If I'm going to bombard you, or you're going to capture something, it goes on the left, doesn't it? But what if you're going to decay? Then it's just you, and you're going to turn into something and something, isn't it? All right, let's do the next one. Is this capture or decay? What do you think? Decay? Okay, now find the missing piece. You got it? Tell me. Oh, we're getting there. So I always have new stuff. I got new stuff for you. Anyway, so let's take a look. What number goes on top here? 0 plus what equals 81?
81.
Plus 1 plus what equals 37?
36.
And look over here at 36 and krypton. Put krypton here. And you're right. Let's answer the question first, then I'll talk about this, okay? Is this capture or decay? Okay. How would you write this out in words? How would you write this out in words? Anybody want to try it? All right, try it, EJ.
Rubidium transmutes into one positive.
Rubidium, which isotope?
8137.
Rubidium 81.
Transmutes into krypton in one positive.
It decays into what?
Krypton in the positive.
Which krypton?
81.
81. And what kind of radiation though?
Beta.
Right. All right. Now, we haven't talked about this yet, but remember the other day I said that when you have too many neutrons, and you say, well, how do you know how many too many neutrons? And I'll talk about that today also. A neutron by itself, or a neutron that's not trying to hold a nucleus together, can decay into a proton and one of these, a beta particle. Now, that's kind of weird, isn't it? And if that ever happens, then you actually will go up. Your atomic number will go up by one, won't it? But what about this? What about that? What is that? What is that? And that's another matter. So protons, that's another matter. Antimatter. Now, the theory of that is that if you take a proton and you throw away the positiveness of it, you're left with a neutron. And that's weird. Now, I will tell you that it's not like that can happen, but I can tell you that in a billionth of a second, after an anti-electron or antimatter, as soon as it runs into matter, they'll both annihilate each other. That's another question that some physicists talk about. What happened to all the antimatter? Why is our universe mostly made out of matter? Why don't we have half matter, half antimatter? What happened to all the antimatter? That's a great question. Now, we can make antimatter. We can make it, but you can't put it in a container. It'll destroy. They'll annihilate each other. But you can put it in a different kind of container, one that's not made of a solid, but it's made of fields, a force field. So if you had a force field, you could put any matter in there, and it wouldn't come in contact with any matter. And then if I could keep it away from matter, I could do things with it. Of course, if you watch Star Trek: The Next Generation, you know the Data has a positronic matrix. Isn't that right? What's that all about? He doesn't run on electrons. He runs on positive electrons. This is an electron that it's a positive charge. That's a positron. Oh, yes.
Why annihilate? What do you mean?
So the theory is that all the matter would change into energy. It would just, and so you might think, well, why didn't the whole universe do that? And, well, God, it wouldn't have been very good for God to make a universe that annihilates itself. But anyway, that's the theory. They're both gone. All the matter's gone, change in energy, like that. Yes?
It's what you call beta particle, right?
Okay. Now, the reason I don't want to call it a beta particle is because it doesn't have a negative charge. So they had to come up with another name, and they called it positron. I think they could have called another one negatron. They could have, but they didn't. But this one's called a positron. All right, let's do the next one. Ooh, let's do the next one. Now, after you fill in the box, see how good you are at writing it out in English. And again, please try it. Even if you make a mistake, you're going to learn something from it.
This may be a stupid question, but why do we write, if we know that each element has to have a certain amount of protons, why do we write the number of protons?
Why do we what? Okay.
Because like krypton's always going to have 36 protons.
Well, the problem is, that's a good question. Every book I've ever read on nuclear chemistry, if it's not nuclear chemistry and you say hydrogen 3, okay, that's all you ever see is the mass. But in a nuclear book, they'll always put that there. Now, I don't know, that's a good question. They didn't have to, but they are assuming you have a periodic table handy and you knew that hydrogen was 1 or something like that. So maybe that's why they do it, just to, do you happen to memorize that krypton is 36? I don't. So I think that's what they're doing there, because you have to balance both sets of numbers, so that's why they tend to write both sets of numbers, a nuclear person.
Okay.
All right, now I don't have these memorized, so Gabby, Allegra, you can help me, okay? What do you got here?
So first,
That's 7, right? So 4 plus 3, yes. What do you have at the bottom number?
that's 3 plus what gives you 2.
How much? So 3 plus 0. 3 has to equal 2 plus what?
1.
Okay, so what is this? What element has 1 proton?
Hydrogen.
Yes. And this is that famous, or sort of famous, isotope. What's the name? They only gave names to hydrogen isotopes. They only have real names. That's one called U-235. See? What's the name of this hydrogen isotope? Ooh. Somebody, what? Tritium. Excellent. Excellent. Anyway, tritium is the only radioactive isotope of hydrogen. That we do use tritium in nuclear bombs. We actually do need to produce, it's not out there very often. Out of 1 million hydrogen atoms, maybe only 3 are tritium. Takes a while to collect a lot of tritium, doesn't it?
US version.
And we have to collect it because we use it in nuclear warheads. We don't have to have nuclear warheads, but the other countries have them. And so we have to make sure we don't run out of, we're always producing tritium. Because about every so many years, they have to replace the tritium in the warheads. I remember one time, there was a headline in a newspaper, and this was before newspapers got to be so political. But it said, U.S. running critically low supply of tritium. Well, first of all, how many people out of 100 even knew what tritium was? Almost nobody. And then, if you knew the United States was running low on tritium, and you knew that we use it to make to recharge our nuclear warheads for the trigger mechanism, why would you tell everybody? That's weird to me. That's weird to me. Why are you telling everybody that, you know, we can't, as all the nuclear warheads we have, we don't have enough tritium to, why would they do that?
How did they even know that?
Well, that's a good question. Somebody knew, they said, well, hey, you know, we had an explosion here in this plant that makes tritium, you know, we're not going to be able to keep up with the demand of tritium because it takes a while to collect a lot of tritium. In World War II, before World War II, I mean during World War II, the Manhattan Project, it took like 2 years to separate all the isotopes of uranium and said, here's a block of uranium. A few of those in there are U-235, and that's what's good for bombs. Well, we need a bunch of them. It took 2 years to make 2 baseball size of U-235s. 2 years. Now, if right now we have people that do that. That's their job, is to make U-235. But just like Iran, just like Iran, Iran says we need a nuclear. We need to make U-235. Why? We don't want you to have a bomb. You've already told me you're going to wipe Israel off the face of the planet if you have a chance. Well, why would we want you to have a nuclear bomb? Oh, we're not trying to make a nuclear bomb. We want nuclear energy, just like you, just like India. We want nuclear power plants. Huh. You're sitting on top of 500 years of oil, and now you want nuclear power. Huh? I really believe you. I believe you. So, of course, what happened when they cranked up their centrifuges, and what they do is they vaporize uranium, and it's really hot, and they spin it in a centrifuge. Okay? So what happens? Who goes to the outside? The heavy isotopes. And then they get separated, see? Now I can separate. That's what centrifuge, when you hear that centrifuges are going, that's what they're doing. They're separating the isotopes. So I get just U-235. Well, one year, I don't know how this happened, somebody got into the computer system, and there's a virus. And the virus made the centrifuge run at way, way, way higher than they're supposed to. It broke them. Darn. Who did that? Okay. Now, so whether or not it was Israel or whether or not it was the United States, it doesn't matter, really. But that's what happened. And luckily, it took them a couple of years to, or at least a year, to get those back fixed because they broke them. And then you probably heard on the news about, let's make a treaty with them. Okay, if you promise not to do this for the next 10 years, then after 10 years, you can make a bomb. That's stupid. That's stupid. We're not going to do that. Again, they're going to say something like, well, you have it. Why can you have the bomb and we can't? India has it. Japan has it. Israel has it. China has it. Russia has it. Why can't we have it? That's a good point. Good point. Maybe it's because you're told that you're going to wipe people off the planet, you know? maybe that has something to do with it. I don't know. And I'm sure they could point to different things in everybody's history. Say, why should China have it? They're known for killing lots of people. Russia? Did they kill a lot of people? Remember that? What, early 1900s? Who's a history person?
Stalin killed 20 million people.
Should they have the bomb? They killed their own people. You You think they'd hesitate to kill somebody else?
China killed almost 60 million.
What now?
China supposedly killed almost 60 million.
But we may not know, but I could see it.
It's somewhere around that number.
So, you know, I understand what they're saying. Why can't we have it? Because you have it. But on the other hand, I think we're going to make it so they probably don't get it. I think they'd use it against us. I really do. I think that'd be one of the first targets. Israel would be the first target, and we'd be the second one. But they might try to fool people, and we'd be the first target. Then they might do something like that. All right, well, let's go ahead and how do we get into that conversation? Oh yeah, tritium. That's right. Can you write this out in words? Ready? Lithium-6 isotope is what? How do you say it? Bombarded, or you can say capture. Neutron by neutron radiation, okay, and transmutes into helium-4 plus hydrogen-3, also known as tritium. Let's do the next one. This one's a little tricky. All right, watch this now. 144 plus 90. 6 neutrons. Wait, each neutron's 1. You have 6 neutrons. That's 6. Here, put in your calculator. 144 plus 6. That's 150. Plus 90. That's 240. Plus nothing. That looks like 240. Okay, so 1 plus what is 240?
32, 39.
I'm doing this in my head, so please tell me if I made a mistake, okay? Bottom numbers. 58 plus 38, it'd be 98 minus 2, 96. 96, 6 times 0, don't worry about that, 96. 2 times minus 1, minus 2. That'd be 94. Oh, that was a 0, that's good. So 0 plus 94 equals 94. What element are we talking about? Ooh, plutonium. Ooh, bad stuff. Does that work? You see how I did that? So each neutron, and by the way, you have to know your characters, okay? An alpha particle is the same as a helium nucleus. A beta particle is here. Unless it's a positron, then you have to do that. And what's a neutron? A neutron has a mass of 1, but it has to be a 0 to make all this work out. And what's a proton? What would a proton symbol be? An old book might have this. But almost all your new books, they have a proton as being the same as a hydrogen nucleus. Whoa, wait a minute. Yeah, that's a 1. Hydrogen nucleus. So that's a proton. All right, now let's try. This is a little bit harder, okay? You have to do 6 and 7. Do that. See if you can do that without any help. And then I think we're going to move on. So see if you can do 6, 7, and 8 without any help, and then we'll see what happens. So 3 kind of tricky questions here. Some books would say francium transmutes by alpha radiation, so or giving off alpha radiation or something like that. So what we do know is that it's going to produce these guys, right? Alpha particles. Now we just have to find the missing link. 208 equals 4 plus what?
204.
Okay, and 87 equals 2 plus 85, what element is that? Is it acetine? Okay. What do you think about that? Not bad? How about the next one?
For all these, we've only had one particle that's that
Yeah, you're right.
how that works,
Um,
or?
I would have to let you know
Okay.
something like that. When we do fission and fusion, I'll show you one of them where it produces producing 3 neutrons
Gotcha.
for every nucleus. So, all right, next one, beta emissions. Beta emission. So which side of the arrow are you going to put it on? Argon 37. I don't have that one memorized. Argon is 18. Okay. And again, it's not capture or being bombarded, so I put it on the right-hand side. And beta, it didn't say positronic, so I just going to put that one. Okay, 37 plus ES equals 0 plus 37. And 18 has to equal -1 plus 19, doesn't it? 19, so who's number 19? Potassium. What do you think? And the last one's tricky. So anybody want to take a chance and say they think they know what this one is? This one's a hard one. Ooh, said Lolly, what do you think?
I think it matters.
Okay. Tim, what do you think? What? Wouldn't be a neutron because a neutron is a 1 and a 0. And I think this guy would be what? Huh. 0 and 0. Sorta. It's not nothing. If you were sitting in that room, it wouldn't be nothing.
What is it, photon?
What is it?
Light?
Yes. All right. And what kind of radiation is probably one of the most deadly forms of light? Gamma. So in this case, we didn't lose any mass, but we did it did emit gamma radiation. So, and that's always the one that's the one you want to stay away from if you can. But we actually do use radiation. We purposely point radiation at light, high energy, either X-rays, we could use gamma rays, but we purposely aim this kind of light at cancer tissues. You know that? When people say they're getting radiation treatment, that's what they're talking about. It's a machine that's going to make a high energy beam of light, and other imaging show that you have a tumor 1 centimeter past your temple and line you up, and they go ready, and it focuses the beam 1 centimeter deep. Now it will cause some of these cells to be damaged also. And the problem with it is the machine can't say, are you cancerous? Me. Are you cancerous? No? Okay. It can't do that. So it just has to take the imaging and said, this mass of cells, most of them are cancerous. So just wipe them all out. Wipe them out. And we probably did wipe out some of the good cells, but we think we might have gotten all the bad cells. So that's called radiation treatment. The other kind of cancer treatment is called chemotherapy. Chemotherapy is where you usually some kind of thing you drink or eat, and unfortunately it goes everywhere. It goes everywhere in your body, and so I didn't have cancer here, but it's making my arm feel that's unfortunate. But sometimes you get to the point where if they think this cancer went from here, went to here, and went some other places, then they may do chemotherapy. They're trying to kill as many cells. I hate to say that. They're hoping your immune system will kick in also, but chemotherapy tends to make your immune system not work as well. So sometimes you die of something else.
So it makes more sense to use radiation
It does.
on tumors
Yes.
versus a cancerous tumor.
And it has an effect. You start killing a bunch of cells, your body will react to that and say, hey, what'd you just do? What'd you just do? And it's going to react to that too. There's going to be side effects of both of them. Hair loss, like you've heard about people. So a lot of other cells got hit. They might not get with a concentrated beam, but they got hit. So there are pros and cons to both. I don't if that happens to me, I'm not sure. I'd probably, the radiation might be okay with me. The chemo, I have to think about it. Chemo does a lot. It makes you, I don't know, you don't, your life's not really quite the same until you stop taking chemo. All right, is everybody okay on this? I'll show you something I thought was kind of interesting. They have a nice color picture of this in your book, even though I probably won't use the book because I've run out of time. But if you want to see a nice color picture of this, it doesn't photocopy all that great, but what this is a chart of all the known isotopes. So imagine all the known isotopes, and I number them, like if you, all the known hydrogen isotopes are going to be here. All the known isotopes of calcium would be here. See that? So all the known calcium isotopes will be here. And their number of neutrons would be here, okay? So, yeah, go ahead. Now, so what's this graph supposed to show? Why are some isotopes stable and other ones are radioactive? How come some of them will sit there for 10,000 years and carbon-12 will be carbon-12? It's not, I'm not changing. And yet, carbon-14 has a known half-life of being 5,370 years. And so about half of the carbon-14s would decay into another element in 730 years. Okay. Why is that? Why are some of you stable and some of you unstable? Why does any atom decay? Anyway, so let's think about it. And here's what, and humans like to try to, I'm not saying this is the answer, I'm just saying they try to answer questions, and this is one thing they came up with. Notice that when you're small elements, oh, by the way, the dark ones, everybody see the dark ones? The dark ones are stable nuclei. The ones that are less dark, and I hate this, it didn't photocopy all that well, the ones that are not dark, heavy dark, those are radioactive isotopes. So take a look here, and what do you notice here in this little band between elements 1 and 20? Notice that we have a lot of stable isotopes, and they have about the same number of neutrons as protons. This line shows a 1-to-1 ratio. This line shows a 1-to-1 ratio, and you can see how a lot of the stable isotopes of the little guys are pretty close to that, right? Carbon, 6 protons, 6 neutrons. See that? Now, what happens, though, as you get bigger? As the nucleus gets bigger and the number of protons gets bigger, what's happening to the most stable? Is it going to be a 1-to-1 ratio, proton to neutron? Or what's happening here? Tell me what you think. We seem to need more what? If you're going to be stable, you need more neutrons, a lot more neutrons than protons. And what about here? And it was a 1-to-1 ratio here, and here it's about a 1.5 to 1 ratio. So if you're one of the big atoms and you have like 60 protons, you probably need, what's 1.5 times 80? You're going to need at least 80 neutrons to be stable. What's that all about? Are you okay on this? I'm just saying this is what they looked at. Why? This is called the band of stability, or the zone of stability. And that's why, I don't know how they did it, but some scientists think that when you get to element 125, it's possible that somehow you could get another band. Notice that I don't have any dark numbers after 83. Huh? What's that mean? No isotope of any element 83 on, as far as we know, is stable. They're all radioactive. For a scientist, and this is a theoretical physicist, to theoretically say, but I have somehow around 125, it's possible there could be a new zone of stability. And I don't think it's going to happen in my lifetime. I'm not sure. It's possible in your lifetime. We'll see.
What makes them think that again?
I'm not a nuclear physicist. I read an article, and they said some nuclear physicists believe that around 125, they could have could find a bunch of elements that are stable. They're not radioactive, which I think is weird. I think it's weird because after 83, you don't find any. I don't find, one uranium is stable. No. So anyway, I want you to see that because it's kind of neat. I want to ask you this question too. Okay, what kind of radiation would you think might happen? If this guy, these have way, way, way more neutrons than protons, don't they? So what's the chance that, could they have some neutrons that aren't quite busy? They're not doing anything? Could they decay? What happens if a neutron decays? What kind of radiation do you get there? Yeah, beta? And what about these little guys? That's asking a lot for a little guy. A little guy, let's say carbon. I have 6 protons and 8 neutrons, all right? I am radioactive, but what kind of radiation am I gonna give off, Would you expect helium to ever be alpha emitter? Wait, helium is an alpha particle. So there's no way that helium is gonna be an alpha emitter, is it? All right, so I'm gonna show you one more thing, then we'll find it here. Okay, here's some more practice problems. I got this out of conceptual physics, and if you want to do some more, you can. I do like some of the little cartoons he did. Thorium late. I overslept. Okay, that's what that says. How about this one? Nuclear physics is the same to me with the first 2 letters interchanged. What's that mean? Unclear. Okay. I thought it was kind of funny. Anyway, that's practice. Here's some more practice, and we're going to talk about fission and fusion a little bit later on. All these are practice. Okay. All right, so now what I'll do is show you. This is kind of fun. And I will have this, I will put one of these on the test just to make sure you can do these. But I did not create any of these series, this pattern here. All I can do is read up on somebody who discovered they're called decay series, okay? So a decay series is unique to each isotope. Okay, so what we're gonna do is, here's how you use this chart. This is atomic number, and this is atomic mass, okay? Or mass number. So we're gonna start with what element? What isotope are we gonna start with? Uranium-235, that's a bad guy. We'll find out he's very fissionable. They would use him for bombs, U-235, but he's radioactive, of course. So let's start with, what is the atomic number for uranium? 92? Okay, so let's go up here to 92 block, and then let's find, its mass is 235, right? So let's put that right here, right on this line here, okay? So I'm in the block for 92, and I'm on the line for, wait, 235. Oh, it's right here, I'm sorry. It should be here. So we're going to put U, 235, 92. Okay, there we go. Is everybody okay now? Now what I want to do is, it says that, I didn't do this, uranium-235 goes through this many steps before it's not radioactive anymore. Step number 1, it'll undergo alpha emission. Now, what do you think is going to happen there? What do you think happens to any element that gives off an alpha particle? What happens to its mass? Goes down 4. What happens to its atomic number? Goes down 2. So let's do it. Ready? Let's go down 2, and let's go down 4. Okay, so let's see if I'm in the right place here. 231. There you are. There you are, 231. Right there. And so I know it's going to be 231.90. But who is that? Who has the atomic number of 90? Okay, let's put that there. Now I'm going to draw an arrow. Okay, so the arrow shows that that's where it's going. What's the next one? Beta. Now you haven't thought about this before, but what happens if something gives off a beta particle? Beta. Beta particle is this. What's going to happen if I give off one of those? What's going to happen to my mass? Nothing. What happens to my atomic number? It goes what now? It goes up by 1. So 231, still 231, but it becomes the element that has the atomic number of 91, which is protactinium. Woo, don't get to see that very often. Protactinium. Okay, try the next one, okay? And I'll do one more with you, and I'll let you do the next one. The next one's alpha, and I didn't do this. They discovered that after this decays into that, and it has its own half-life. You know that? The rate at which that occurs has a different half-life than the rate at which that occurs. And then this guy, protactinium-231, is going to do what? So I got that done. It's going to be alpha emitter, isn't it? So what's going to happen to that? He's going to lose 2 protons, 89. So I'm going down to 89. I'm going to lose a mass of 4, right? Which is 227. 227, 89, there we am. And 227, and who in the world is 89? Oh, actinium, yes, actinium. And I'm going to draw an arrow. All right, well, go ahead and try that, and see if you can finish it. And the final question says, what isotope is the final product? Let's see if you can come up with that, and then look at your neighbor and see if they get the same one. And when they get to the final product, that means that that thing is stable. That isotope is stable, and no further decay will occur after that. Yes?
We go to 89 or 90?
Uh-oh. Oh, which one? Did I make a mistake here?
I think the next one.
Well,
We went from 91 to 89.
Yeah.
You put it.
Oh.
Put it up 90. Should it be one over to the left?
oh, dang it. I made a mistake, sorry. It's over here, right?
Yeah.
Thank you very much. 230, what's my mass? 227?
Yeah.
And 89? All right, my fault. Sorry, good catch. Good catch. Anyway, try this, and then when you get done, look over your neighbor and said, are you done? And if they shake their head, say, what'd you get? What's the final isotope that is not radioactive? It's going to be stable. Does anybody know what would happen if you had a positronic emission? Ooh. What if you gave off a positron? You wouldn't lose any mass. But what? Would you go to the right one or go to the left one? Since you said both answers, you're right. But which one do you want to stay with? Yeah. Okay, so if a regular beta particle makes you increase your atomic number by 1, you know why? Because a neutron turned into a proton. But what's a positronic emission do? It turns one of my protons back into a neutron. Now I lose a proton. Now, even though we haven't done fission and fusion yet, I think right now you could probably pick up a book on nuclear, anything that has to do with nuclear energy or something like that. You could probably understand it a whole lot better now. Now, we do need to talk about fission and fusion. That's what I'm going to do next time I see you. We will talk about creating energy. Why? How can you create energy with fusion and fission? And I don't think you're going to like what you're going to hear. And since I only have 1 more minute, let me tell you what's going to happen. Did you know that if I had 10 marbles, 10 red marbles, 10 blue marbles, and I weighed them individually, and then I put them together in a bowl, how much would it weigh? If I had the mass of all 10 particles, all 20 particles, and I add them up, and I put them in a bowl and weighed them, subtract the weight of the bowl, what would you expect? Wouldn't that be the same?
Or if not, if they're all different sizes.
Yeah. No, I could weight them. I weighed 10 marbles. I wrote them each down. I weighed 10 blue marbles. I weighed them down. I added them together, and I put them in a bowl and weighed that, and they'd weigh the same, wouldn't they? Well, you're not going to like it on Monday when I tell you that the mass of a proton, when it's not in the nucleus, is 1 AMU. And the mass of a proton, when it's in a nucleus, is not 1 AMU. If I told you had 5 protons and 5 neutrons, wouldn't it weigh 11? Not going to. And what you're going to find out is this: it's going to find out some of the mass was converted into energy. E equals mc squared. You're gonna find out that you lost mass. You didn't lose it. It was turned into energy, and that's the energy that holds the nucleus together. And when Einstein said, there must be a tremendous amount of energy holding a nucleus together, it was big. It was big. When he said E equals mc squared, do you know the speed of light is already a big number? And when you square it, it makes really big. So even a little mass, a tiny bit of mass changing to pure energy is huge. Okay, what's the isotope name go? Tell me the isotope name go. Lead 207? Very good. Very, very good. All right, thank you very much. All right. You have a nice weekend. I won't see you tomorrow. So
this particle emission step is for all almost all that, or just
that it just so happens that U-235, that's the series of decay. Now, if I had another isotope, I don't memorize any of these series, but I'd have to look up what the series is for another isotope. Okay.
Why would it be 207?
What now? So what should have happened here is every time you had alpha emission, you would go kind of like a diagonal like this, you know, and beta, you would go to the right. And so,
I got lead for after for
yeah, you should have lead, but what isotope of lead? Whoops. Well, see, wait a minute. Yeah, you should have had a beta, alpha, beta. This looks like alpha, alpha, alpha. See, look, here's alpha, beta. Alpha, so you're
I
right.
needed another alpha.
Yeah, here's alpha, here's your beta. And now you should have two alphas in a row. Boom, boom. Wait a minute, I don't see your arrows. Is that going over here?
Yeah.
Are you talking about 81?
Then you go beta, then you go beta.
That's an L.
Then you go three alphas in a row. So you
That's
should have gone from here. Should have gone from here. Alpha, alpha, alpha. And then you would have gone a beta, alpha, beta, and then stop it.
Oh, okay.
You can do it again.
Is it emitting a beta particle or a beta positron?
Beta radiation is a beta particle, but not positron. I'd have to use the word positron.
Okay.
So if I say beta, you know it's just a regular one with negative charge.
Stephanie, I'm just wondering, did you know you're putting that extra credit in? The extra credit packet?
Wait a minute. Yes. Let me turn this on.